Welcome back for the daily LeetCode day 1000. Now it would be cool to get to day 1000, but it is more like day 183. So we are back once again. Today's definitely a tough one. Definitely, we have to do an hour. Something about the hour sessions has been working well, so we have to stick to it. I think this is for a long while. We've actually been doing 1 hour a day for about actually quite a long time. So almost since the end of November 26th, and it has proven to be very useful. So that's been pretty good, and I'm trying to keep that as the minimum so 1 hour never feels like a chore. So hopefully we can keep doing that. I did only 45 minutes of game dev yesterday. Actually, no, it was like 30 minutes on camera, but off camera, it was more like 4 hours. So it is progressing very well. So hopefully it'll be a smash hit, and then EA is gonna call me in. They're gonna say, or Epic's gonna call me, and they're gonna say we're taking Fortnite offline to put this game on. So hopefully that will be what happens. But we'll definitely have to see. But what we will have to see about for certain is the comments. So we do have some comments. We have a comment from Ashish Kushwaha. Try Grovbox theme. It's pretty cool. True. Many a time used in Vim users. A lot of Vim users use that. We have a comment from Daksh. Never stop the grind, bro. Rooting for you, fellow LeetCoder. Remember, good things take time and patience, so keep on pushing. We all will reach our goals one day. Facts. Let's go. Yeah. So this is a must. It is a necessary evil to battle in the Colosseum to reach the end of the Gladiator series. So fortunately, somehow with the LeetCode we're making progress. We're at 250, which I think means that in the grand scheme of things, 250 times 10 is 2,500. So technically, we are 10% of the way complete with the journey. So, I mean, you can't beat that. So, well, a lot of people have beaten it. Also, a lot of people have finished the journey. So, but it's just to say it, we're making progress, and I hope everyone else who's also doing LeetCode is also making the progress they hope to make. So, that is really all we can do, is show up every day and have some kind of slow growth action. Change takes time. So, what else can be done about that? It does indeed take time. Even we think about from like a perceptual learning perspective, the fastest way to learn is to have literally practice that is geared for exactly what you want to learn, and then you can try the thing, and then something will immediately give you feedback and say yes or no. Even that process, although fast, still takes a lot of time, and that's like the state of the art. So definitely making progress, but we just got to keep at it. So it'll be very interesting to see where we are 365 days from now. So yeah, maybe by then we all have UBI and ChatGPT has liberated us from our suffering. But we shall see. But I'm just going to jump into today. And yeah, it's just another day, another dollop of suffering, another day to battle in the Colosseum. We're broken. We're weary. We're tired, but we must forge on anyway. So, yeah. So, things are actually speeding up. I didn't think we would speed up this quickly, but we actually are speeding up. So, maybe the easy problems are getting better, or maybe there's a set of problems that we're used to now that we can just kind of blow through. And I definitely feel that way about some array problems. But, yeah. We are stuck on a backtrack problem, though. I'm going to give this one another hour and then another hour tomorrow. And if we haven't figured it out by then, although I think we'll figure it out today, but it remains to be seen. I also need to start uploading earlier, because I noticed there was a cheat code there. If I uploaded around 11 a.m., it's literally the golden hour for some reason. But if I upload later in the day, the video is almost dead. So more things to do. I wonder if I should push this one back and upload it tomorrow. That way it'll still be daily. It'll just I have pushed it back one day because we're doing it right now. No, actually, you can't do that without skipping a day. So I'd have to record 2 days. Yeah, so that's interesting. Yeah, it's actually unfortunate. And yeah, we're gonna have to get the music situation sorted out as well because this intro is not flames. So yeah, I'm definitely tired. So we just got more to think about and more to do, and there's not much else to do but to just get to work. So we're gonna jump into it as per usual. Daily LeetCode guy, and I'll start the timer. We're going to do an hour. Unfortunately, I'm going to be honest. It's definitely unfortunately. This is definitely one of those days where I don't want to do an hour. But we have to do it anyway. So I think the problem that we're working on is, right, sum of all subset XOR totals. The XOR total of an array is defined as the bitwise XOR of all of its elements. Bitwise XOR of all its elements, or 0 if the array is empty. XOR total of an array is defined as the bitwise XOR of all its elements. XOR total of an array is defined as the bitwise XOR. Or 0 if the array is empty. For example, the XOR total of the array here is 1. Given an array nums, return the sum of all XOR totals for every subset of nums. Subsets with the same element should be counted multiple times. Subsets with the same element should be counted multiple times. Subsets with the same elements. Wait a second. There's no way they mean that. So you get the right answer for case 1, but we're off by 2 for case 2, and we're also way over for case 3. Subsets with the same element should be counted. Subsets with the same elements should be counted multiple times. Subsets with the same elements should be counted multiple times. So they're saying if we have 561 and 165, we should count them. an array A is a subset. An array A is a subset of an array B if A can be obtained from B by deleting some, possibly 0 elements of B. So let's try a different example. We have 516 here. We're going to add up all 8 subsets. 516 is 1. Each individual number is 1. They have 5, 1. They don't mean that. They said all the same subsets will count, but they actually don't mean that. Because if that was the case, then we'd also count 1, 5, and we're not counting 1, 5. So 5, 6 is an XOR total. So let's see if we can follow what's going on here. What we'd like to happen is we'd start at 5, right? We'd view it as a graph where each vertex has an edge to every other node in the graph. Each vertex has an edge to every other vertex in the graph. So we'd start at 5. We've seen 5 already because we're saying we saw it. And then for each state of the DFS, we'll try to retain the state of that call when it was called. Try to retain the state for that node, for that vertex when it was called. So when we call for 5, when it's called for 5 here, we'd like to go from 5 to 1. Right, we retain the state of 5, and within 5, we'll say, okay, let's visit all the nodes we haven't seen yet. One node we have seen now that I'm realizing, we're automatically adding it to the scene. This one, which we pass in, should basically be DOA, because we're copying the value. Or it should be DOA. We'll actually see. Let me do scene. Let's say what we'd like to happen first. You'd go from 5, retain the state. Then we go from 5, right? Cur XOR is starting at 0, XOR 5. Right, we're now going to DFS into 1 here. Well, we can't DFS into 5 because we've already seen 5. Right. Now we're going to DFS into 1. We DFS into 1 with the cur XOR. And then we say, okay, well, what's our XOR at? Well, cur XOR is going to be equal to 5 XOR 1, which is apparently 4. Right? So in this new scene set that we have at 1, we've seen 5 and we've seen 1. So we're going to skip these two nodes, and now we're going to check node 6. What we haven't seen, we're going to go into 6, right? We're going to say, okay, well, cur XOR, right? We're going to do 516, which is going to be 2, right? And we've seen everything here, so we're going to say O.sum plus equals 2. Now we're going to come back up, exit this node in the tree, or this tree that we're viewing of this call. Go back up to 1. 1 is just now visiting 6, right? It's coming out of this loop right here. So now it's going to add 5 XOR 1, right? And it's going to be coming out. So now we have, if we just copy this whole thing, right here, we can say which ones we have. We have 516. We have 5-1. Right, because 6 was that last one it visited. We do O.sum plus equal cur XOR. Then we would propagate back upwards to 5, right? And now we would check with the scene set that that 5 has, right? So with that, when it has, we have 5 ones. We're going back to 5. And technically, we would visit 6. Now, is that what is actually happening? When we view this case as a test result, we're in 5, right? We're in 5. Now we're going into 1. Now we're in 1. We've seen 6. Right, we're in 6, and we're saying cur XOR at, which is the number we're at, and the number is 2. 5 XOR sum of this array is 2, which is good. Right, then we have, we're at 1. The XOR of 5 and 1 is 4. Right, we're in 5. Now, we're seeing 6. 7, 1, 6. We have 5. We have a 3. We have 1. We have a 4. Problem is we have an extra 2. And I think I see what we need to do. This is good because we're generating all the ones that we need. Now we just need to make sure that we're seeing every version of this where the order is changed. So if we have 5, 1, 6, we're also seeing 1, 5, 6, 6, 1, 5, 6, 5, 1, which is not the wave. This is ending up in extra calculations. It's messing things up. Maybe what we could do is make sure that we don't do something like we could make sure that we don't if we add a specific chain of nodes together, if we've seen a subset of these nodes before, we don't want to add it to the sum. If we've seen a subset of this, for this path we're taking through the graph, if we've seen this collection of nodes used before, we don't want to add it. The issue there is, though, actually, wait. Right. Actually, maybe this can be avoided. Because when we go from 5, what's happening is that we're going and checking out 6. Well, maybe we shouldn't check out 6. Right? Maybe we shouldn't check out 6. So when we go to 5, we've only seen 1. And in fact, we haven't really seen them. We're just not going through it again because of the loop. What if we're just not going through it again because of the loop? So if we stay in the loop, if we don't stay in the loop, if we think about how we're going from 5 to 1 to 6, back to 1, back to 5, there's no way to propagate that upwards. Well, there is. We just wouldn't make a new set. We would just keep seeing. But how does this change how this works? If we start at 5, we go from 5. We add 5 to the set, right? We've already seen 5, we'd go to 1, right? We'd add 1 to the set, right? Then we'd visit 6. Add 6 to the set, we XOR our sum, we'd get XOR total of 6, then we're going back up to 5. Well, actually, yeah, we'd be in 6, right? And there's still nowhere else for us to go. We'd go back to 5, and since they're all sharing the same set, there'd be nowhere else to go. And then we'd go back up to 0, or we wouldn't go back to 6 again. What's to stop us from starting at 1 and going 1, 5, 6? If we add 5 to the set, we're basically saying don't use this again. So we don't have to do scene.add I because when you go into the DFS, it is added. Same for scene.add here. And then I think the difference is that you would still give each node a new set to start with, so that would just be a copy of scene for which we would add I. The only other way I can think about this is to go back to the other way where we're severely overshooting it and then make sure that the subsets that we do see are the subsets that we add to the XOR are unique. So let's try that. We would pass in scene. And each set would get, I don't know what just happened. But each set would get a copy of scene instead to preserve, to give it a new state that it can preserve. This version should get us back to overshooting, which it has. And then from here, the goal will be to keep the chain going. So the chain will be an empty array, or we'll just call it subset. It'll just be an empty array. We can add one more parameter, subset, which is a number array. And we'll have another one called subset scene, which is going to be a set of strings Oh, I see what's happening. It still thinks it's part of this object. And so what we can do now is we can say subset dot push nums sub index, right? And then we can actually just print our current path by printing subset. And the way we can make sure that this doesn't get destroyed on each run so that they all don't share the same one, because an array is an object, we'll just copy it for subsequent calls. So we should get the same output we've been seeing. So now we should be able to tell our path a little bit. So path is 5. We're going to 5 to 1. Actually might be better if we do it like this. All right, in 5 scene 1, then we go 5 to 1. In 1 scene 6, we go 5 1 6. Cur XOR at. Actually might be best to do it in here. In 5 scene 1, right, and then it goes through 5 1, and then it sees 6. We go through all 6, then we're like, okay, well, nothing here. We could say XOR is for path so XOR is 2 for path 5 1 6. Cur XOR is 4 for path 5 1. Right, and this is the extra 2 for 5 6 1, which is what I was saying. 5 6 and then 5. So all we have to do is basically convert the subset to an ID, and the way we'll do that is we'll take the subset we're just going to sort it. Actually, we can just say subset dot sort, and then subset as ID will just be subset dot reduce we'll say prev No, they're already numbers. What you'd have to do, it makes more sense to just turn it into a string and then just join them. And then we'll say if subset seen does not have subset as ID, right? Then we want to add it to cur XOR, and then we'll also do subset seen dot add subset as ID. Now the runtime of this should be absolutely abysmal. But they should have a lot of space for us to not get TLE, because it's an exponential algorithm. Oh. One, one, one. There's only one. One, one, one. And one, one. What do they expect here? The answer is 4. Oh no, unless they don't really care about the numbers we use. Maybe this is what they meant by that piece earlier. Subsets with the same element should be counted multiple times. What they're trying to say here, I think, is that it's the nodes that we should be using as IDs, not the actual numbers at the index. So we should, I guess what I'm saying is not the numbers in the array, we should be using the nodes IDs, because 1, 1 in the current way we're counting still counts as 1. 1, 1, basically if you look at the first one and the second one, right, that's the same in our algorithm as the second one and the third one. These should be 2 different ones. And a better way to do that is, instead of pushing the number, we'll just push the index itself instead. Then we can still sort them. Wow. Our output limit exceeded. Okay, so this is actually good. Let me remove all these outputs because this is exponential. We're literally looking through every possible permutation, and that should be 12 factorial, which is like 479 million operations in the worst case. So our version still takes too long. Could use a better heuristic to prune the tree, and we're getting closer to an answer. This one actually solves it, I'm pretty certain, but it takes too long, which is unacceptable. So I think this is not acceptable. I'm wondering if with this whole, one of the issues is the sorting thing. I guess our path can at most just be 10 nodes wide, which in the worst case, it's not that bad for sorting, but we're sorting many times. Maybe another way to prune the search tree is instead of using the subset as ID, to use the cur XOR. Yeah, I figured that was a dangerous one. Hmm. 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 Today was progress, though. We did. I'm pretty sure all the tea leaves we're getting means we're actually going about it the right way. But our search space is way too large. Oh, the search space is already large. Maybe there's a way we can prune the search space. Oh, well, we could actually. What am I saying? We have the path up here. We can just say if we've seen. Well, actually, no. If we say we've seen this path before, for example, 1, 6 versus 6, 1. Or actually, right. If we have seen this path before, it is a duplicate path. Once a number is finished processed, presumably all the permutations with that number we already have. So what we can do this up here. The other thing we can do is say subset seen dot has subset as ID. We can just return. And this is already much faster. Oh my god. Oh my god, there is a god. There is a god. No way. That is incredible. That is actually crazy. That is actually crazy. I believed. Yeah, so I'm seeing now we learned a couple things about backtracking. The first one being after the first permutation, after visiting the first node and visiting all its permutations, we've already visited every possible path that includes that node. So there's no point if any node ever adds if any node ever has that suffix as its path, that's prefix as its path, we've already seen it. Yeah, that was crazy. Backtracking. Yep, backtracking, combinatorics. Let's ingest this. Oh, it's not even a premium solution. That's crazy. Why use backtracking? One of the indicators from the description to use backtracking are the words all subset. Looking at the constraints, the length of the input array is relatively small, so we can approach this question using brute force. First, we generate all the possible subsets from the input array. Then, for all calculated subsets, we calculate the XOR of all elements in each subset, return the sum of all calculated XORs. Generate all possible subsets. We can recursively generate all possible subsets given an array. For each element in the array, you'll have two choices. Include the current element in the array in the generated subset, or withhold the current element from the generated subset. So you're going the step-by-step approach. We would store all the subsets in a list, calculate their XORs. However, this is not necessary, as we can calculate the ongoing XOR total while generating the subsets. The trick is to be able to remember the state of the current XOR that is calculated for each recursive step. We did do that. So you're not explicitly storing the subsets in a list. We just need to return the sum of the calculated XOR when the current element is considered. We're not explicitly storing the subsets in a list. We just need to return the sum of the calculated XOR. Yeah, his solution is, or this person's solution is very elegant, but it's pretty crazy. You can either include the current element or go without it. If you go without it, you still move forward. I'm not gonna lie, this person beasted on this problem. Subsets recursive sums. If index is equal to the length of nums, return term. We have term and index. Otherwise, we return sum, term, comma, idx plus 1 plus terms x, or the number at the current index. This is crazy. I think it's like the other person said, you can either include or you can exclude. You can either include you can either include the element or exclude the element. Sums of term comma idx plus 1 plus sums. I said sums. Sums term XOR. Start with 0, you go idx plus 1. If idx is equal to the length of nums. If idx is equal to the length of nums, it means we're done. This just ends the loop. Because at minimum, the first one always guarantees that we continue, that we exclude. And the second one guarantees that we include. Start with 0. We have two choices. We can go to the next one. Or we can do 5 XOR 0. We do 5 XOR 0. We can just go to the next one. It's actually very powerful because at each point when we have a subset or a path, we always try and include. For each path, we basically always choose include another element or don't. Since we're going forward through the array, this sort of ends up happening naturally. My issue with this is how do we make sure that we don't actually... Does this only make new combinations? How does it make sure it doesn't retread old steps? That's what I don't understand. Subsets recursive. They have subsets iterative, bit manipulation, math-based one-liner. That was interesting. That's a good problem, though. That was a good problem, but I think we will stop there for today.